Hello students, welcome back to my channel. You are watching All Over Physics. In the previous video, we completed the solved exercises from chapter 1, that is Introduction to Physics of class 11. If you have not watched the video yet, make sure to check it out first for a better understanding of the concepts. In this video, we are diving into the exercise questions from the same chapter. Since the exercise is little bit lengthy and detailed, we are breaking it down into three parts, and this is part 1. We'll solve the questions step by step with clear explanations to help you understand the concept thoroughly. So grab your notebook and let's get started. But before proceeding further, if you find this helpful, please like, share, and subscribe to the channel for regular updates and more such videos. We'll take the first problem. The problem states find the dimensions of linear momentum, frequency, and pressure. So one by one, we'll find the dimensions. First is the linear momentum. Linear momentum is a vector quantity and defined as the product of the mass of an object and its velocity. Momentum is always in the same direction as its velocity vector. So formula of linear momentum can be written as P is equal to mv. Linear momentum is denoted by the symbol P. M is the mass of the object and V is its velocity. Now we have to find the dimension for linear momentum. So we'll write within square bracket P is equal to within square bracket M and V. Now if you remember our previous videos, dimension of mass is represented by the symbol capital M and dimension of velocity is L t to the power minus 1. Therefore, altogether we can write it as ml t to the power minus 1. Now, next is frequency. Frequency is the number of occurrences of a repeating event per unit of time. Let us look at the figure. A waveform is propagating along the x direction. T is the time period, that is peak to peak propagation time. In another way, we can say that in t seconds, the number of variation is 1. Therefore, number of variations in 1 second is 1 by t. And we just told the number of variations in 1 second is nothing but frequency. Therefore, you can say frequency, which is represented by the symbol f, is equal to 1 by t. Now we can write t is proportional to m to the power a, l to the power b, and g to the power c. Here, g is nothing but acceleration due to gravity, which is L t to the power minus 2. Therefore, we can write the equation as m to the power a, L to the power b, L t to the power minus 2, and there is a c exponent. So, rearranging, we can write it as m to the power a, L to the power b plus c, and t to the power minus 2c. Now on the left hand side we have only the time period t. Therefore equating we can write a will be 0, b plus c will also be 0, and minus 2c will be 1. Therefore we can write dimension of time period as m to the power 0, l to the power 0, and t to the power 1. Therefore dimension of frequency will be 1 by m to the power 0, L to the power 0, t power 1, that is m to the power 0, L to the power 0, t to the power minus 1. Now we'll find dimensional formula for pressure. Pressure is force per unit area. Therefore, we can write pressure is equal to force divided by area. force is equal to mass into acceleration. Therefore, dimension of F will be dimension of m and dimension of acceleration. And we know m is represented by the symbol capital M, whereas a is L t to the power minus 2. And down we have area, so dimension of area is L square. Therefore, altogether we can write pressure, dimension of pressure is equal to m L t to the power minus 2 divided by L square. Therefore, it is m L to the power minus 1 t to the power minus 2. Next problem is also similar to the previous problem, where we have to find dimensions of angular speed omega, angular acceleration alpha, torque tau, and moment of inertia, that is I. And the corresponding equations are also mentioned in the problem itself. So first we'll take angular speed. Angular speed is a measure of how quickly an object rotates or revolves around an axis. That is, a rate at which angle of rotation changes with time. Let us look at the figure. There is a wheel which is rotating in this particular direction. Suppose at time t1 it is making an angle of theta 1, and at time t2 it is making an angle theta 2. Therefore, we can write angular speed, which is denoted by the symbol omega, will be change in angle divided by the time duration. Or other way you can write delta theta divided by delta t. Now we have to find the dimension of omega. Therefore, we'll write within square bracket omega will be equal to square bracket delta theta divided by square bracket delta t. Now, delta theta is an angle, and angle is dimensionless. So how come it is dimensionless? For that, we'll draw a part of circle, and this is the center of the circle, and we'll make two lines which will intersect them at x1 and another at x2. Now this is an arc. Suppose the arc length is s and it is making an angle of theta, and r is the radius of the circle. Therefore, we can write theta, that angle will be s divided by r. Now, if we take the dimension of delta theta, now s is a length, therefore it will be L, and r is also length, therefore divided by L. So if this cancel out, and what remains is m to the power 0, L to the power 0, t to the power 0. Therefore, we'll write delta theta is equal to m to the power 0, L to the power 0, t to the power 0. Now comes delta t, which is nothing but time. So time is represented by capital T, or other way you can write m to the power 0, L to the power 0, t to the power 1. So we'll put this in the main equation. Therefore, we can rewrite the dimension of angular speed omega as m to the power 0, L to the power 0, t to the power minus 1. Next is angular acceleration. Angular acceleration is the rate at which velocity changes over time. So if at time t1 angular speed is omega 1 and at time t2 angular speed is omega 2, then we can write angular acceleration, which is represented by alpha, will be change in angular speed over the time duration. Again, we can write it as delta omega divided by delta t. Now we have to find the dimension, that is within square bracket alpha will be delta omega divided by delta t. Just now we have derived dimensional formula of angular speed as m to the power 0, L to the power 0, t to the power minus 1. And dimension of time is denoted by capital T. Therefore, we will write m to the power 0, L to the power 0, t to the power minus 1 divided by t, that is equal to m to the power 0, L to the power 0, t to the power minus 2. Next is torque. Torque is the twisting force that causes rotation. Now let us look at the figure. A mass m is pivoted to the axis of rotation through a rod of length r. When a force F is applied, it starts rotating around the axis of rotation, making a circular path. Then torque can be written as tau is equal to R cross F. Now we have to find the dimension of torque, that is tau. So first comes the R part, which is nothing but length. Then come force. Dimension of force is mLt to the power minus 2. Therefore, we can write dimension of torque tau as mLt to the power minus 2 into L. That is mL square t to the power minus 2. Now we'll take moment of inertia. Moment of inertia is a measure of an object's resistance to changes in its rotational motion. Equation of I is mr square. So on the right hand side, first we have mass, which is represented by m. Then we have r square, which is nothing but radius square, and radius is nothing but length. Therefore, we can write it as L square. Therefore, dimension of moment of inertia is equal to m into L square. In other way, we can write mL square t to the power 0. Now we'll take problem number 3, where we have to find the dimensions of electric field E, magnetic field B, and magnetic permeability mu naught. And the relevant equations are F is equal to QE, F is equal to QVB, and B is equal to mu I divided by 2 pi A. And as usual, F is the force, Q is the charge, V is the speed, and I is the current, and finally A is the distance. First, we'll take electric field, that is E. Now, electric field E is equal to F divided by Q, where F is the Coulomb's force and Q is the test charge. So you have to find the dimension of electric field. So on the right hand side, first we have force, and we know force is denoted by mL t to the power minus 2, and then comes the charge Q. If you remember our second video, there we have derived dimensional formula for charge, which is nothing but I into T. Therefore, altogether we can write dimension of electric field E is equal to mL t to the power minus 2 divided by IT. So rearranging, we can write mL t to the power minus 3 I to the power minus 1. Next problem is magnetic field. For a long straight wire carrying a current I, the magnetic field at a distance A is given by the formula B is equal to mu naught I divided by 2 pi A, where mu naught is the permeability of free space, I is the current, and A is the distance. Similarly, magnetic force acting on a moving charge Q is given by F is equal to Q V cross B, where V is the velocity of the charge and B is the magnetic field. Now we got the equation F is equal to Q V cross B. So taking B on the left hand side, we can rewrite the equation as F divided by Q into V. Now we have to find the dimension of magnetic field B. So on the right hand side, first we have force, and force is denoted by mL t to the power minus 2. Then we have charge Q. The dimension of Q is equal to I into T. And then we have velocity, and as you know, velocity is denoted by LT to the power minus 1. So putting all the values in the main equation, we can write dimension of magnetic field B is equal to mL t to the power minus 2 divided by IT into LT to the power minus 1. Therefore, rearranging, we can write m t to the power minus 2 I to the power minus 1. And we also got magnetic field P is equal to mu naught I divided by 2 pi A. So taking mu naught on the left hand side, we can rewrite the equation as B into 2 pi A divided by I. Now just now we got dimension of B is equal to m t to the power minus 2 I to the power minus 1. And then comes the term 2 pi, which is a number, therefore it has no dimension. Then comes A is nothing but distance, therefore it will be denoted by L. Then comes the current I, whose symbol is also I. So putting all the values in the main equation, we can write dimension of magnetic permeability as m t to the power minus 2 I to the power minus 1 into L divided by I. Therefore, rearranging, we can write m L t to the power minus 2 I to the power minus 2. Now we'll take problem number 4. The problem states find the dimensions of electric dipole moment P, magnetic dipole moment M, and the corresponding equations are P is equal to QD and M is equal to IA, where D is the distance, A is the area, Q is the charge, and I is the current. If there are two charges, one is positive charge that is plus Q and another is negative charge that is minus Q, and they are separated by a distance D, then the electric dipole is represented by P is equal to Q into D. Now we have to find the dimension of electric dipole moment P. On the right hand side, first we have Q, dimension of Q is equal to IT. The next term is distance D, it is nothing but length. Therefore, dimension of electric dipole moment P is equal to IT into L. Therefore, we can write it as LTI. Then comes magnetic dipole moment. For a current loop, the magnetic dipole moment is calculated as the product of the current I flowing through the loop and the area A of the loop. Therefore, we can write magnetic dipole moment M is equal to I into A. Now we have to find the dimension of magnetic dipole moment. So first we'll take current. Dimension of current is I, and then comes A. A is nothing but the area, therefore it is L square. Therefore, putting this in the main equation, we can write magnetic dipole moment as I into L square, or in another way, we can write it as m to the power 0 I L square. We'll take the next problem. Find the dimensions of Planck's constant h from the equation E is equal to h nu, where E is the energy and nu is the frequency. Now we'll learn in details about Planck constant when we'll read the relevant chapter. So we'll find the dimension. We'll write the equation E is equal to h nu. We have to find dimension of Planck constant. So therefore, taking h on the left hand side, we can write the equation as E divided by nu. Therefore, we have to find the dimension of energy E and then nu, that is frequency. Now, if you remember our second video, there we have discussed about the dimension of energy. So we'll repeat that part again. Energy is the ability to do work. Therefore, dimension of energy, it will be equal to dimension of work. Now we know work is equal to force into displacement. Now dimension of force is ml t to the power minus 2 and displacement is length. Therefore, altogether we can write dimension of work as ml square t to the power minus 2. Therefore, dimension of energy is ml square t to the power minus 2. Therefore, we'll write it here. And just now we have derived the dimension of frequency, which is m naught L naught t to the power minus 1. Therefore, putting these values in the main equation, we can write dimension of Planck constant as m L square t to the power minus 2 divided by m naught L naught t to the power minus 1. Therefore, it is m L square t to the power minus 1. Alright students, that's it for today's lesson. I hope you found it helpful and learned something new. We'll start our next video with part 2 of the exercises. If you enjoyed the video, make sure to hit the like button. And if you are new here, don't forget to subscribe the channel for more contents every week. Thanks for watching all our physics. See you in the next video.